Alright, today I'm going to do a quick video giving an example of building a module in EvilVM, and that's going to be for keystroke injection. So keystroke injection is one of those kinds of things you want to do. Sometimes when you're working on someone else's box, you get access, they have a login session somewhere that you care about, and you can cause the system to simulate keystrokes at the keyboard so you can interact with their applications live. And this relies on really two key functions in the Win32 API. One is keyboard event, and this allows us to simulate or inject key down events and key up events for keys on the keyboard. And then secondly, we need to be able to convert from characters from strings to virtual key codes, and that's going to rely on the VK key scan function. And with these two, we can put together a keystroke injection utility and then make this useful from the interactive REPL sort of shell context that we've got with EvilVM, and that should make it pretty easy to use for effect when we're compromising some other box and working with it in an assessment. So to get started with that, we want to pull in some information relevant to these functions, and we'll start with the list of constants. I already pulled this out from the documentation. I really just pulled this down from Microsoft's website and then convert it syntactically so that each of these is a constant definition. So these are the hex codes for each of the V keys. Once we have that out of the way, we need to import the user32 DLL, and from there we're going to pull in two functions. So first we use loadlib to load user32.dll, and then that puts the base address for the DLL on the stack, and we want to assign that to a constant. And then for each of these two functions, we want to pull them in. And for example, we've got the VK key scan function. This one takes a single argument, and that's all we need to know to write the wrapper for this. So we'll put the base of the DLL on the stack. We'll indicate that it takes one parameter. We'll call it DLL fun, and then this takes two names. One name is the function name for the fourth side, and the other is the function name in the DLL that should be imported. So in this case, we'll call it VK key scan, which is its proper name, and we're specifically importing the ASCII version of this, not the Unicode version, so capital A on the end. And then the other function that we need to pull in for this is the keyboard event function. It takes 4 parameters, so that looks relatively similar. And this gives us enough to be able to call these functions now from a fourth context. If we want to see what that looks like, let's hop to a handy EvilVM session, and we'll load this code, these definitions. And if we look at the dictionary, we can see these all came in. We have all these virtual keys, and we've got the couple of functions that we've imported from user32.dll. So let's call one of those. Easy one to play with is VK key scan. What we would give it is an ASCII character, so maybe we'll just give it the code for the letter A and then see what comes out on the other end. So this one's interesting. If you look at 321, you might say, well, that's an odd number for the letter A. If we do a small a, we'll see that comes out as 65, which is much more what we'd probably be used to. If we look at these in hex, though, it'll become obvious what's going on here. So the capital A is a 41 hex, but then in the second byte there's some extra information that indicates that it's shifted, so it's a capital. If we do a small a, we'll get the hex 41. So there's a little bit of extra information in a virtual key code, and when you're playing with the keyboard event function, it doesn't necessarily interpret this correctly, so we have to do some work to type capital letters correctly, and punctuation marks that are the shifted versions of numbers, and we'll get into that in a minute. But here you can see we've imported these functions. We can call them. They're giving us what look like reasonable responses, and this should be enough for us to be able to create keyboard events so that we can press keys on the keyboard. So the next thing we'll do is we'll define a couple of functions for pressing and unpressing or releasing keys. So the way this is going to end up looking is we're going to make a couple definitions. We use colon to define new words. And to press a key down, we're going to need to know what the virtual key code is, and we'll use that up. So this stack picture shows that the word expects to have a virtual key on top of the stack, and it's going to use it up once it's done. this is just straight up a call to keyboard event. And so it takes four parameters. The first one is a virtual key. The second one is a scan code. As long as you have the virtual key right, you don't actually have to use the scan code, at least as far as I've seen using keystroke injection in real life. And then there's a flag variable or flag parameter which says what kind of event this is. And you just leave it as 0 if you're pressing the key down. The value 2 is for releasing a key. There's another value that is really irrelevant to what we're doing anyway, but those are the two values that we care about. And finally, there's an option to send a pointer to an extra information variable, but we don't really care about that either. We just want to generate the keystroke event, and then we can call keyboard event directly. So in EvilVM, DLL-Fun wraps up each of these functions, and it just assumes that all functions return a value, so it'll put the value in the A register on the stack. But in this case, this is a void function, so it doesn't return one. So we drop that. And then actually, this is enough to do a key down event. Key up looks very similar. The only difference is that this flag needs to be a 2, so we're saying it's a key release event. And that's enough to do key up and key down. We can put these together and we can make a, let's call it keystroke. We'll take a virtual key and we'll issue the key down. We're going to need to do a key down and a key up, so we need 2 copies of this virtual key code. So we'll duplicate it, we'll do key down, and then we'll wait just a little bit just so that the key presses are actually at somewhat realistic time differences between each other. I don't know if it matters, but just in case something is watching the frequency of key presses, we want to make sure everything looks halfway reasonable. And then we'll issue the key up, and maybe we should wait another delay after that. So this should give us enough actually to start typing keystrokes. So let's give it a shot and see if we can make sure this is working for us so far. So switching back to our session, let's test this out and see if we can type something. We remember that the letter A was a $1.41, so let's issue a keystroke and test this on Windows box. So this is the machine where we're running the agent right now. So I'll execute this, and we get an A out. So that's encouraging. So that shows that this keystroke function works well for us. We could type other things, but we'll quickly run into some issues. Like one interesting example is, say I want to type a greater than sign. So we're going to take that, and I have to convert this to the virtual key, so VK key scan, and then I want to issue the keystroke. We'll switch over to our other box and see how that comes out. We see that it comes out as a period, and that's because it's the shifted version of the period, and keyboard event is a little bit more simple than we would want it to be able to send just any regular ASCII character as a keystroke. So we have to shift on our own, so we'll issue a shift down, and then we have to type the correct virtual key for that character, and then we issue a shift up, and that would enable us to type it. But there are a whole bunch of those. There are lots of characters that don't come out right if we don't do the shifting. So we have to account for that and do something about wrapping up keystrokes with shift down, shift up around them. So the way we're going to do that is we're going to define a wrapper. So this is going to be something that we can tell it around some sequence of key presses we want to have this other key pressed and then get it released when we're done. So we'll call that with key. And we need to know 2 things. One is what we're going to do while it's wrapped, and then which key is wrapping it. So I'm going to do this with a higher order function where we're just going to take a function and we'll execute that in between the key down and the key up. And then we need to know the virtual key of the modifier that's going to wrap around the other keystrokes. So we're going to use a little bit of a trick here. This is kind of shady in the fourth world, but it's something that you can do if you understand what you're doing. You just have to be a little bit careful. So when you look at most fourth code, you should pretty much have observed the stack behavior. We put values on the stack, then we call functions. Functions consume data from the stack, etc. And that's the parameter stack or the data stack. There's also another stack, which is the return stack. This one keeps the return pointers for nested function calls, and that's how we get all of the execution model of regular code with fourth. But we can also use that stack. If you're used to languages like C, local variables and other things can often get stored on the stack, and of course that's the source of buffer overflows or basic stack overflows and things like that too. In Forth, the stacks are separated. There's a parameter stack and a call stack or return stack. But we can use the return stack as a data stack occasionally, and that gives us something that we can do. We need to keep a copy of this virtual key around while we run the function, but when we run it, I want it to be able to see the stack that was there when the programmer's code was running. And so this way we can kind of hide this value and make sure that the way the programmer experiences it is what is expected. This might make sense once I use it in a sec, but so what we're going to do is take this virtual key code and we're going to send it to the return stack. And then immediately we're going to read it off the return stack without eliminating it. These are standard words in Forth for interacting with the return stack. And then I'm going to key down that key. So now we've pressed, like if we're shifting to get capital letters or punctuation marks, we've now pressed the shift key. And then what's on the stack is the function that we're going to call. So we'll execute that. And then we'll pull the V key or virtual key back off of the return stack onto the data stack, and then we'll key up it. And again, just in case it matters, I don't want to press the key down and then instantaneously have some other code running another key press. So we'll put a little delay in here just in case it matters. Probably doesn't, but who knows, just in case. So what this will enable us to do is wrap up some series of keystrokes with another key press. And I'll do a couple examples of this so that it's obvious what I'm talking about, but I think this ends up being a kind of useful idiom. So let's hop to the shell and let's reload our definitions. And then from here we can try this with key. So let's try capital A. So we are going to do a keystroke for code number 41. And we'll do that along with the shift key, something like this. So hopefully we should see on our test box that this comes out with a capital A, and it does. So yeah, this allows us to shift characters, and if we go and try something else, like we did that greater than symbol, right? So we do key greater VK key scan. So this ends up being a 446 is the right code for that. So let's do a keystroke. That's the virtual key for it's both the period key and the greater than symbol key. And we'll shift it with something like that. And hopefully we'll see a greater than sign come out. So yeah, and if I do that without the shifting, we get the period out. So this way we can properly shift keys and get all the characters we need. But we need some way to represent which ASCII codes need to be shifted. So capital letters need to be shifted, small letters do not need to be shifted, and they're scattered all over the keyboard. So we need to come up with a strategy for that. What I decided to do is define a table of flags, and each flag indicates for a given ASCII character whether it should be shifted or not. So we're going to do that with what is basically an array. In Forth, you have definitions. So we've been using colon to define words, which are basically functions. But you can also define other things in the dictionary. And as a general purpose tool, the create function just creates an entry in the dictionary by name, and that name is associated with its address. So it creates a pointer. So we'll create a pointer to an array called table, and then immediately after its definition is the point where the pointer points. And so after that, we'll allocate space for 256 bytes. There are 256 possible ASCII codes if we're using 8-bit ASCII. And so we'll make space for a flag for each one of those. And by default, we'll start these all out at 0. And so we'll use the fill function. It looks basically like a memset. So we're going to fill them all with zeros. We're going to start at the table address. We're going to do 256 of them and fill up the data there. So at this point, we have a place where we can store all of these flags. We also need to populate it with the data for which characters need to be shifted. And we can do that kind of just a quick pragmatic way by defining a string that has all of the shifted characters in it. And this is really easy to make because we just, of course I'm going to try to talk while I do it. Just type in everything with the shift key down, and this should give us a list of all characters that need to be shifted. There we go. And I need to escape this one so that these all end up being in the same string. The Emacs fourth mode doesn't properly understand \escape quotes because that's not normal for most fourths, but EvilVM supports it, so don't mind the fact that the green highlighting stops here. This is a valid string. What we're going to do is go through each of these when the code loads, and we're going to populate that table with flags for each of these characters to show that they need to be shifted. We can do that a couple ways. One important thing to recognize is that strings in fourth are represented as more than just a pointer. So C uses null-pointed strings, null terminated strings, and other languages have more complex data structures for representing strings. In fourth, the way it works is if I have a string like this, we put that on the stack. We see that it's the base address is a pointer to the H in hello world, and then a second value, which is the length of that string. So generally strings are what are called counted strings, and so we have to keep track of both of those. And it's not uncommon that we want to be able to iterate over all of the characters in a string or all of the bytes in a memory region. So there's a useful idiom or shortcut function in fourth called bounds, which takes a region in memory like a string and represents it as the two ends of a counted loop so that you can iterate across them very easily. So we use bounds, and that sets up a do loop. So it's going to be something like this. And in the loop, the I counter variable, which is the counter for the innermost loop, is going to be in each iteration a pointer to one of the values in this region of memory. So this is a pointer, so we're going to read the character at that pointer, and then that's the character that needs to be shifted. So we use that as an index to the table array, right? So we start at the base of the table array and add that character value to it, and then we're going to set that value in the table. So now we should have a 1 value in all of the slots that correspond to the letters that need to be shifted. So that's kind of a mouthful. Let's hop over to the shell and see what that actually looks like. Ooh, and actually, before we do that, I realize I have a bug here. So we want to have an actual value to put in there. So we need to start with a 1 on the stack, then find the address and memory of the place for that flag to store, and then store it. So try to make sure we get that in there too. And there we go. All right. So let's hop over to our shell, and we'll reload our definitions, and then I also want to load another sample that has a pretty hex dumper utility. So let's take that table and look at the 256 values in it, and we'll make sure that that looks right. And so here we see that for some of the values in the table we do not shift them, but for some we do. And since they're kind of scattered all around, there's not really a pretty way, at least as far as I have figured out, to represent these that's any better than just doing it the way I did to define a string that has all those characters in it and loop through it. So that gives us a way to represent how each of the characters needs to be shifted, and that gets us one step closer to having a general key press that just takes a character from a string and prints it out or types it out at the keyboard. So the next step is to write a more generic. Right now I have keystroke, and that takes a virtual key. So we want to write up a generic function that is going to type out a character properly. We'll call that press. And press needs to know, for example, if the character needs to be shifted. It's going to take a character and type it out to the keyboard. So we're going to test to see if that character is shifted. So we make a copy of it. We use that as an index into the table, grab that flag, and we just use that in an if conditional. So if it's true, if that flag is set, then this character needs to be shifted. And so what we're going to do is, you know what? Actually, there's one thing that's missing here, is decoding the scan code. So let's hop up here real quick and think about this. With a keystroke, we're taking in a V key, and actually we maybe don't want to do it exactly that way. Let's make this, instead of keystroke, we'll just call this V key for typing a virtual key, and then keystroke is going to take a char, and we'll look this up with the vk keyscan function like that and call vkey. Okay, so there we go. That way, when we press the key, we can wrap around the keystroke function to type that, but with the shift pressed around it. And then if it is not a shifted character, so it doesn't have to be capitalized or the shift key pressed when we type it, then we can just call keystroke directly. And so that should give us general conversion from ASCII characters to a keystroke. So let's test this out and see if we made some useful progress. So we switch back over to our shell. Let's forget all the definitions. We've loaded a few times, I think. Load our keys. And so now we should be able to just type out all of the ASCII keys, I think. So let's do a quick single character test just to make sure. We'll do a capital A key press. So switch over to our test box, and we get an A out. Let me try this with a greater than sign. Yep, that worked. Let's try it with a period. Yeah, that worked too. Cool. So we're shifting when we need to. We're not shifting when we don't. And we're getting keystrokes out, so that looks like it's working great. Let's write up another quick little one-liner to just run through the whole alphabet with all the punctuation marks and everything else and see if this is working. So ASCII, 7-bit ASCII ends at 126. And we'll say it starts at 32. That won't include the new line and the tab character and stuff like that, but this will give us a good test anyway. So we're going to take the character and we're just going to press that key. So this actually should print them all out. Let's give it a shot and see how this looks. There we go. And we got capital letters, we've got punctuation marks. If I didn't have this shifting logic in there, you'd see repetitions because the same key, when it's not shifted, just or the shifted and unshifted version of one key would both have the same character. So this should be enough to type general things out, but it's a little bit annoying to have to take a string and pull out the characters, or even worse is to find out all the V keys for how you want to type something. So let's make an API layer that simplifies this a little bit for the programmer, makes it easy to send strings to the keyboard while we're interacting with the target box. So one way to think about this is we just need a way to send a string to the keyboard. So we might have something like, so the normal function in Forth to print a string to the standard output is the type function, be like that. But in this case we're going to type it out to the keyboard, so we'll call it key type. And what this might look like is we get the address of the string and its length, and we're going to print it out at the keyboard or type it out at the keyboard. So we use that same idiom for iterating across a region in memory. And actually with this, each time we iterate, we get the address of the next character in the string. We'll read the byte from that location, and then we'll type it. Actually, that should be enough for us to do something like this, where we can say, you know, define the string hello world. Let's put the new line in there, and key type. And let's see how that looks. If we go back to our session here, we can reload our definitions, switch over to our notepad here, and let's just run test, T-E-S-T, and we get hello world in the new line. So that's a pretty easy way to send strings out, but I think we can actually do this one better. We can make it even more accessible to the programmer and do some interesting things with it. So let's take this to the next level. So while this is okay, we can actually wrap this up and do a little bit of metaprogramming, and I've said several times in other videos that the Forth compiler is a programmable compiler, and so you can change how it does things when it's compiling. So let's make a little compiler for keystroked strings, and so we'll turn this into something that looks a little bit prettier and ends up making a little bit more sense for somebody who's operating EvilVM like a shell and not so much like they're writing a program. So we'll define a new kind of string called a key string, and that starts with the key quote function. And what we're going to have this do is actually turn this code, or generate this code from something like this. So the key quote function will compile the following string and then add in or compile the call to the key type function and kind of make the workings underneath here invisible to the programmer. And the way we do that is we say, well, the first thing it has to do is invoke the same functionality as the string definition function, which is squote. So we'd like to do this, except the problem is that squote is an immediate word, so it also is an extension to the compiler that adds the ability to represent strings. And what will happen is when I run this here while we're compiling keyquote, is it will run and try to define a string in the keyquote function. But that's not what we want it to do. We want keyquote to wrap up the functionality of squote and define a string when it gets run by the compiler later in the user's code. So there's a special function for this. We can use postpone. What postpone does is it takes in the next word in the stream, and it compiles this so that squote doesn't get run by the compiler here, but will get run by keyquote later. So we can kind of undo the fact that this is a compiler extension and treat it more like it's a regular function. And so squote now will run when the user's code executes it. And then once that's done, we want to compile a call to key type. So this is a really simple example of how we can write these extensions to the Forth compiler and add new, what is essentially syntax for defining a new kind of string, and get that into our code. So this makes this look fairly pretty, in my opinion. We don't have to think about how that's actually getting there. And so now the user can kind of use this as a command as long as it's compiled into like an anonymous function or something. So if we save that, we'll hop over to our session and see if it works. All right, let's load our code again. We go back to our test box, and then we're just going to run test. And we see that hello world comes out just fine. And so one of the interesting things we can do with this is, as we use it in our code, like say we wanted to do something which is actually fairly common in the post-exploitation scenario that we would use keystroke injection. Maybe we got hold of a remote desktop session, or maybe it's like a KVM session or something like that on some box, and we're able to use the keyboard. So what we're going to do is, from the desktop, we're going to run, say, a command prompt or something like that. So we're going to define a function that types the letter R, and then maybe it waits a second, and then it types CMD and presses enter. And then we're going to wrap that up with the left Windows key. So what this is going to do is press the Windows key. Actually, you know what? We don't want to do it that way. We want to do it more like this. So we're going to wrap up a key press of the R key. Then we'll wait about a second. Make sure that the run dialog can come up. And then we're going to type out CMD and press enter. Does that make sense? I hope. So we've got this anonymous function, does the R keystroke, and then it's going to get wrapped up with the Windows key. We wait a little bit, and we're going to type CMD and press enter. And that should give us a command prompt on the target machine, hopefully. So if we go look at that, I'll run this code. And then there we go. So now we've got a command prompt. And when we go back, we can do something like keyquote ipconfig. I don't know what we want to do here, but we'll do something like this, and we can interact with the machine. Oh, and of course we forgot to press enter, so that's okay. We can do it a couple ways. 10 press is probably the easiest way to do it because that's the ASCII code for a new line. And so here we have a completely usable keystroke injection utility, and it's all written from Win32 API code for just a couple of functions, and it does pretty much what we need to. We could dress it up some more and add some more things, but this is actually quite functional. I'd be happy using this if I was doing a pen test somewhere and needed to do keystroke injection as it is. So that's it. I hope I did okay in the video. I made a first run at it, and it was so long. I just thought there's no reason to have a video that long. Hopefully I didn't accelerate it too fast. If you have questions about it, go ahead and say something in the comments. And I hope to do more videos like this just to show the workflow when operating through Forth, through the EvilVM environment, and doing regular hacking type activities. So anyway, thank you for watching.